Okay, so today I want to talk about rule 2 of the method of brackets. So I gave I made a video about rule 1, where we used it to compute the Gaussian integral in, I guess, only one or two steps. And today I'm going to talk about rule 2, which is the multidimensional extension of rule 1. And what it says is the following. If you have this multidimensional integral in the following form of several sums, and the summand needs to have this very particular form, which is not at all unreasonable. So it's going to have a sequence G, which depends on each of the indices, as well as a dependence on, obviously, the variables here. And let's see, what's the best way to write this? X1 to the alpha 1 n1 plus alpha nk plus beta 1 minus 1. I need another index here. So I need, let's call this alpha 1, 1, and this one will be alpha 1k. All the way up to xk, and here we will have alpha k1 n1 plus alpha kk in k, and there's a plus beta k minus 1 in that exponent. And of course, there's the differential here. Okay, what's this? All right, so what we want to do is compute this integral, and the method of brackets tells us to just ignore convergence once again and pull the sums outside. We'll pull out all the constants as well. And what are we left with? We're left with several integrals of, let's see, x1 to the alpha 1, 1, n1, and so on. And instead of writing all the other ones, I'll assume you get the point here. And there's some other stuff and a dx. Okay. So the other thing is this guy here. Okay. So what's left here is several brackets. So remember, we formally defined the integral of this x to some power thing as a bracket, where the power appears in the bracket. So what appears here? Well, the exponent does, plus 1. So we have an alpha 1, 1, and 1 through alpha 1k nk plus beta 1. And we have all the other brackets, and it ends with alpha k1 n1 through alpha kk nk plus beta k. Okay, so what do we do with this thing? Well, here's what the rule says. It says to solve the linear system given by the vanishing of the brackets. Okay, so this is not horribly difficult. It's a linear system. These things can be solved with a computer, but let's just take a look at some of the notation that we can use to simplify this treatment. So notice I've written these alpha in a very particular way. They're labeled by two indices I and j, and that tells us that maybe we can construct a matrix given by these coefficients that might be somehow useful. And indeed, we can. In fact, the method of brackets tells us that once we solve the linear system, so let me make an addendum here, solve the linear system given by the vanishing of the brackets for the solutions n1 through nk star. The star just denotes that it's a solution to the vanishing of the linear system. Then the method of brackets tells us is that it's the evaluation of this integral should be 1 over the absolute value of the determinant of this matrix A times G of, let's see, this is N1 star through NK star times gamma of minus N1 star through gamma of minus NK star. And that's it. So the evaluation of this integral, this horribly complicated integral in general, is transformed into the solving of a linear system, which can be done by a computer easily, I'll add. And the solution is just given by this formula here. So notice that this method does not work when this matrix is singular. So that happens whenever there's linear dependence in these brackets here. So the method actually fails when there's linear dependence in the exponents of the variables here. Okay, but that's the second rule of the method of brackets. And in another video, I will introduce the third rule, and then I'll use this to compute what are called the Borderline integrals. So, till next time.